All right, hello everybody. So we're going to be quickly just reviewing some vector addition and subtraction and taking a look at some algebra and the logic. So just a reminder that vectors are simply a representation of movement in some way, or they could be forces. There's different ways that you can use a vector to represent certain things. One of the most logical ones is traveling from one point to another. So for example, you're at point C, which could be, somewhere in your house, perhaps, on the same level, maybe in the kitchen, and then you're going to travel a certain direction to get to your family room, right? Something like that. Or if you're outside and you happen to have a backyard and you happen to be standing on your back patio, let's call that point A, and you walk along a certain pathway in your backyard and you happen to get to a tree or a bush at point B. So just different ways of traveling. So we're going to take a look at the way you would add vectors. So think of it as adding two different types of movements. So moving from one point to another and then moving from that point there to somewhere else or conversely. So here's some algebra. You have AB plus CD. So what this basically means is I want to have a starting movement that represents this here. Oops, get rid of that. This here, so I want to travel in this direction. So the direction really is implied by the kind of like the slope or the gradient of the direction of the vector here. So this vector has this very kind of steepish slope. So you can almost think of it as kind of a, well, it looks like almost like a 45 if you look at it from that point of view. And so here's what you basically want to do. So this is basically saying I want you to travel from point A to point B. Okay, now there's normally vector notation up at the top here. So you want to travel from point A to point B. So you're going to start at a certain point, travel this length or magnitude in this direction. Okay, but then after that, in addition to that movement, you're then going to move in the direction that CD tries to wants you to follow. Now CD wants you to follow in this particular manner. So CD, instead of going up and to the right, CD has you traveling down to the right. Now, in addition, when you add these vectors together, so here's how it looks visually. So we're going to first travel from A to B, and then we want to travel the way this vector is telling us to travel. So when we stop at point B, we're then going to travel in the direction of CD, which means we have to connect these vectors tip to tail, so, or head to tail, whichever you'd like to call it. So the head of this vector, AB, is now connected to the tail of vector CD. So let's see if this makes sense. Travel from A to B, and then in addition to that, after you stop at B, you want to travel in the direction that CD tells you and wind up at D. Travel starting at A, go to B, and then follow the directions of C to get to D. Now, obviously, for most people that say, well, if I'm able to, why can't I just travel from C to D or from A to D? And that's exactly what the triangle law is all about, and there's a parallelogram law. So what you wind up getting then is a resultant algebra. Oops. And it looks like that. So traveling from A to B and then from C to D is equivalent to just starting at point A and going straight to D. So why would I travel these two different directions if I'm able to travel straight from A to D? Well, that's by foot, by car, by airplane, by whatever mode of transportation. These could be forces as well. So an object is pushing one way and different force, or sorry, you're pushing an object a certain direction, there's a different force forcing it to go a different direction. This would be kind of what we refer to as a resulting force or net force. All right, and you'll see that a little bit later on as we get through some of the sections here. All right, so just to change things up a wee bit, but we're going to go a little quicker here. So this says, well, how about if we start with CD, and then we add AB? Well, so now what we want to do is we're going to start at C, travel towards D the way this vector tells us to travel. So this one tells us to start at C, go in a downward direction, that magnitude to get to D. Okay, and then in addition to that, we want to travel in the direction that this vector is telling us, AB. So AB is telling us to travel in an upward direction. So the addition would be, well, once we travel from C to D, then I need to follow the directions that AB is telling me to get to here. So once again, we've connected the tip of, or the head of vector CD to the tail of vector AB, and logically then, this gives us, a solution here where we have vector CB. All right. Now there's a parallelogram law that you can take a look at, because traveling from C to D and then adding AB is exactly the same as traveling AB and then CD. You notice that this black line is pretty much identical to this black line here. All right, pretty darn close anyways. All right, so there's a parallelogram law that shows the equivalence of these types of movements anyhow. All right, so the order that you add the vectors in, whether it's AB plus CD or CB plus AD, so this is AB plus CD, CD plus AB, you get the same resulting vector. All right, what about subtraction? Now, subtraction, a little bit different. Subtraction, here we want to start with following whatever AB tells us to do. So I'm going to start at a certain point and travel in an upward direction at that angle, or north, or whatever convention is being used. But then this concept of negative. So the concept of negative here. So this minus sign implies opposite direction. All right, so here's what this example wants us to do. It wants us to travel the way AB is telling us to. So AB wants us to go in an upward direction from A to B, but then now we have to travel the opposite of what CD wants us. So if CD is here to here, well, what we really want is the opposite of that. Now here you got to be a little bit careful. So the opposite of C to D is, well, as you guessed it, it's D to C. So this algebra then becomes something I can manipulate. So how about if we said AB, but then the opposite of CD is BC. So what I can do then is I can say, well, instead of traveling from A to B and then going the opposite of CD, I can change that algebra to say, well, I can travel from A to B and then I can travel from D to C in that direction. And here's the result that you would get from a visual point of view. And then the overall resulting vector is here. Okay, so again, this would be kind of a resulting vector. So travel from A to D, and then go, or sorry, from A to B, and then the opposite, we switched it around. Instead of going from C to D, the opposite of C to D is D to C, and there we get our result. Okay, so that's how subtraction works. There are some other tricks to it, but logically that kind of makes sense. If you think of negatives as opposites, then things hopefully will work out for you. And in this particular case, we're going to just take a look at, if you're given a shape, what are the vectors you can come up with. So here you're given a polygon, and it's labeled with some signs. And again, the vector notation is kind of missing here. Typically, you would have that, but some textbooks use it, some textbooks don't. Okay, no big deal. Anyway, this algebra is saying, okay, travel from A to B. So I'm going to travel from A to B. But then in addition to that, I want you to travel from B to C. Well, if possible, wouldn't it be easier just to travel from there to there? So that would give me an algebraic expression of, correct, AC. So take a look at the logic. If I want to travel from A to B, and then after that, in addition to, I want to travel from B to C, well, to make my life easier, I can just travel straight from A to C. So from A to B, B to C, I can then just go up straight from A right to C. Okay. Not quite sure how that got locked. Okay, there we go. And then similarly, this algebra is basically saying go from A to B, travel that direction, that magnitude, and then go to B to C. And then lastly, from C to D. Well, I started way over here at A, and I ended at D. So my starting point is A, ending point is D. So this algebraic expression can be simplified to just AD. And again, vector notation would imply you have some sort of notation here. Whoop, that's a bit big. Let's make that a little thinner. Some sort of vector notation up at the top here. Very useful. Some textbooks use it, some textbooks don't. Okay, so it's not necessarily a big deal. And once again, this got a little locked. I'm not sure how this is locking up on me, but anyway, irrelevant. Okay, so the last situation I'm going to talk about is if you have some 3 random points in space. These can be points in your house, points in the field, points in space, points in the air, or just theoretical points. It can be just about anything. So this algebra, so we're going to talk a little bit about the difference between what's happening with this algebra here and what's quite unique about this. So here we're being told to start at point M and then travel to point P. So let's do exactly that. So we will travel from point M to point P. So there's a vector. There's the tail of the vector and there's the head of the vector. But then it's asking algebraically to subtract QP. Now QP is a different vector altogether. QP is there to there. So that's QP. Suppose I just temporarily ignored the algebra and just use some logic. Well, if I'm traveling from some particular random point, M, and I want to go to P, which is a different random point. Now, to get to another random point, Q, we know that this means the opposite. So MP is the opposite, negative QP is the opposite of PQ. So I should be able to do this. And then the result would be MQ. So once again, these funny things seem to be locking up on me for some strange reason. Okay, so one more time. Travel from M to P. There's one direction. Now, if this is point P, I have to go the opposite of point Q to P. So both of these again from M, there's that point P. So it's the same kind of logic, but look at the result. The result is MQ. So let's see how this makes sense here. MQ. Q. How does this make sense? Well, the reason why it makes sense is because I'm traveling from M to P, but I want the opposite of QP, which is traveling from P to Q. So I simply have to reverse this direction. And lo and behold, I get MQ. All right. So there are different ways of taking a look at this subtraction, especially one in terms of an algebraic notation. There's different ways of also looking at the results. So please feel free to view some other videos for enhancement.